We left off with isotopes. I'm talking about isotopes. All right, isotopes are an atom that have the same number of protons, so they're the same element, except they have a different number of neutrons, which then leads to a different mass. By having a different mass, they could have radioactive properties, but they necessarily don't have to have. The majority of my isotopes are not radioactive. They just have a different mass. Why that's important and all of that, well, we can use it in chemical studies, because here's the deal. If I am the same number of protons, I'm the same element, so for instance, if they want to test your thyroid, they could inject you with a radioisotope of iodine. Therefore, they could follow that mass difference of regular iodine you should be taking up versus the heavier or lighter iodine, depending on what they inject you with, and see how much of the isotope your thyroid took up to see your thyroid function. The thing is, your body just sees iodine. It sees the number of protons, it knows it's iodine, so it'll uptake it as iodine. But scientists or medical professionals can see the difference based on the mass. This is if they have radioactive properties, you can use them to treat different types of cancers and things like that too, because again, wherever the cancer is located, if your body will uptake it, and then it'll emit radioactive properties. But our cancer treatments are getting more and more exact, more and more direct, so there's a lot of advancements there. Now, isotopes are the reason that if you look on the periodic table, so what we talked about, all right, in the last chapter, or last presentation, I should say, not chapter, was, well, if I look at something in this form, okay, the AZ form, this is the mass number, this is the mass of the element on the periodic table, all right, but it's protons plus neutrons. But then I go to the periodic table, and I look at the periodic table and I see something like this. I see carbon, I see, the atomic number. Here's the atomic number, and that's the number of protons. But down here, we have the atomic mass. And carbon's 12.01. Well, if my mass number, and my mass is the number of protons and neutrons, which we said it is, how the heck do I have a 0.01 of a proton or a neutron? Well, the thing is, the atomic mass is not the mass number. The atomic mass is an average of the isotopes that are present in nature. And here's what I mean by that. So let's say we do analysis of a sample, okay, of an element. And it doesn't matter what the element is. All right, I'll call it element X. And let's say there's 3 isotopes of X. Let's say there's X33, there's X34, and there's X35. Okay? And we run analysis on a sample of the element X. And what it'll do, we put it in something called a mass spec, and the mass spec will spit out information and give you the exact mass of each component and its percentage. So let's say it says, all right, X33 is present, and it is 92% X33 in our sample. X34, which is an isotope, is 7%, while X35 is 1%. And it'll give us a mass. It'll say, like, this is really 32.99 mass. All right, so here's its percent abundance is what we call it. Here's its atomic mass, 32.99, 34.01, and it actually takes it out to a lot more decimal places. All right, and let's say 35.02. Now, I want to find what the atomic mass of this fictitious element is. What would I report or find on the periodic table? Okay. So here's how we do it. It's an average of this information. So the mass of an isotope, okay, is equal to the sum of the percent abundance times the mass of the isotope. So if I wanted to find, not the mass of the isotope, I should write this as the atomic mass. If I want to find the atomic mass of X, I would do the following. I would take 0.92, because that's the percentage, times 32.99 plus, look at our next one, 0.07 times 34.01 plus 0.01 times 35.02. And if I had more, I would keep this going until I added them all up. And then whatever this equals is what the atomic mass was. So I take 0.92, then add it up, times 32.99, 0.07 times 34.01, 0.01 times 35.02, and add them all up, and that would be the atomic mass of the element in question. Now, in the slides and in your book, sample problem 2.5 is one you should try that does this. Okay, it's all worked out on the slides for you to get the correct answer, and gives you the correct answer, and then we'll assign some homework on it. So the reason that we have on the periodic table fractions or decimals, I should say, is because we're actually taking averages. If it's a whole number, that means there's only one type. There's not multiple isotopes. That also being said, if there are multiple isotopes, the one that's the most abundant will be the atomic mass or closest to the atomic mass. So for instance, carbon is 12.01. There's carbon 11, there's carbon 12, there's carbon 13, there's carbon 14. But carbon 12 is the most abundant, and the reason I know that, since I'm doing an average, and it's a 12.01 reported on the periodic table, I know that carbon 12 must be the most abundant. Oxygen, there's oxygen 16, 15, 17, 18, but oxygen is 16.00 or 15.99, so we know that oxygen 16 is the most abundant. Okay, questions on this, how to find the atomic mass given this information? So percent abundance, which looks like a W here. Percent abundance times the mass of the isotope. You'd have to be given this information. Okay. So after all this is said and done, and Dalton put out his atomic theory, our modern assessment of the atomic theory, everything was correct for James Dalton in the late 1700s, early 1800s of what he predicted based on modern research, except one thing. So all matter is composed of atoms, and they're all unique. He was right there. Atoms of one can't be converted into another. The only thing that Dalton got wrong, and I think I'll give him a pass for late 1700s and 1800s, not knowing about nuclear reactions. Nuclear reactions, we can actually turn, if something is radioactive, an element into another element. Only if it's radioactive and undergoes transmutation, what we call it. But I think I'll give Dalton a pass that he didn't know about nuclear chemistry at the end of, the 1800s. Okay. All atoms are identical in the protons. The only thing, isotopes have a different mass. All right, but they're still identical except for their mass. And compounds are formed by specific chemical ratios. So Dalton was pretty much right on, 200 years ago about what we accept today as the, modern chemistry or modern idea of what's going on. So again, here's our periodic table. Again, I want to point out a couple of things here. Okay? And this is the periodic table that's in your book. Number 1, the majority of the elements are metals. Okay? Number 2, we have the nonmetals, and they're on the right-hand side. Number 3, there's a small staircase there in green, which are known as the metalloids. They're not completely metals, but they're not completely nonmetals. Other things I want to point out. There's something known as the main group elements. They are the ones that are sticking up. 1, 2, 13 through 18. Now, you'll see new numbering and old numbering. The new numbering is in the parentheses, and since that's the new accepted way, that's what I'm going to be referring to. I prefer the old way with 1A, 2A, 3A, and so on. But the majority of books and the majority of science has gotten away. This is one reason I like Silberberg, because they still keep that notation up there. But we're going to number 1 through 18 across. 1, 2, 13 through 18 are known as my main group elements. 3 through 12 are known as my transition elements. And then there's a cutout, and this cutout would essentially stack on one another. So these would all like stack on top of each other and be coming out of the periodic table. And they're known as the lanthanides and actinides series. And they cut out right here because they all act similar. They're called the lanthanides because this is lanthanum. And they're called the actinides because this is actinium. And again, I'm going to tell you this. You should be familiar with your symbols, because if you do not become familiar with your symbols, naming compounds is going to be a little bit more difficult if you have to look at the chemical symbol every single time to name your compounds. Okay, so we have the lanthanides and the actinides cut out on the bottom. 1 through 92 atomic number up to uranium are naturally occurring elements. 93 on. I think we're at like 120 something now, or 119 now. Okay. Let me see. I know they just found a couple more. They just created a couple more in the lab. 118 is the highest atomic number right now. Okay. Oganesson is what it's called. But it was created in a lab, and we really don't have to worry about that. All right, so, but anything after 92 is man-made. Up to 92 are naturally occurring. Okay. This was all laid out, or started to be laid out, by a guy by the name of Mendeleev. And mendelevium, which is on the periodic table, all right, is basically named after Mendeleev. All right. And there he is, Dmitri Mendeleev. Started putting stuff together in the 1860s. All right. And what he would do is every time something acted like hydrogen, he'd start a new row. The rows are called periods, and the vertical columns are called groups. The periods are numbered 1 through 7. The groups are numbered 1 through 18. I mean, there's a myth out there that he was doodling it on. He started doodling the periodic table on a napkin while eating lunch. So think about what you do during lunch, and think about what Mendeleev was doing. Mendeleev was doodling the periodic table. Now, here's the deal. The way the periodic table looks today is not Mendeleev's periodic table. He would leave gaps because he had no idea, because certain elements weren't even discovered yet when he started putting the periodic table together. And we'll talk about this in Gen Chem 2. All right, we'll talk about this in Gen Chem 2 for those of you who have to take Gen Chem 2. All right. So the modern periodic table is not what Mendeleev was working with, but he would leave spaces and he would say, well, there has to be an element that fits here. So there's 3 classes, like I said: metals, nonmetals, and metalloids. Metals are the majority. Metals are solid at room temperature, except our friend mercury, which is a liquid. They're shiny, they conduct electricity, they're ductile, which means they can be made into wire, they're malleable, which means they can be hammered into sheets. They make solutions, all right? Alloys of metals are mixtures of metals, so brass, bronze, pewter, steel, all right, are not elements. They're actually mixtures of elements, metals, okay, to make new alloys. Our nonmetals are found on the right-hand side of the periodic table, except hydrogen, and even some of the periodic tables put hydrogen on both the left and right-hand side to show that they really act like group 17. They conduct electricity very poorly, and the big six that make up our biochemistry are nonmetals, which are copper, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. My metalloids, are also known as semimetals, are the border between the metals and the nonmetals. They have some qualities of metals and some qualities of nonmetals, so they're not completely metals and they're not completely nonmetals. And there's 6 of them that are classified as metalloids: boron, silicon, germanium, arsenic, antimony, and tellurium. All of them make sense with their elemental symbol except for antimony, which is Sb. Okay, and here they're pointing out what some of our metals look like, our metalloids and our nonmetals look like. Our nonmetals, okay, so like our metals are all solid except for mercury. Our nonmetals can be solid, they could be gaseous like chlorine, they could be liquid like bromine. Okay, so it all depends, all right? So my main group elements, like I said, it's going to be important to distinguish between main and transition. My main group elements are 1, 2, 13 through 18. My transition elements are 3 to 12. The reason they're called transition elements because as we move from left to right on the periodic table, we're transitioning from metals to nonmetals. Okay. And then again, the lanthanides and actinides, I explained them earlier, they're at the bottom. And we'll rarely talk about them in Gen Chem 1. Now, the vertical columns, okay, are known as groups. They're also generically known as families. And the reason they're known as families is because everything in a specific group acts similar. They're not the same, but they have a similar tendency on how they act. So some of them have specific names to them. Group 1 is known as the alkali metals. Group 2 is known as the alkaline earth metals. And when we do acid and base in chapter 4, alkali or alkaline, as you see it written here both ways, means basic, non-acidic. And the reason they're called the alkaline metals or the alkaline earth metals, okay, is because both of them are very reactive. They react very violently with water or oxygen. So in nature, you can't go and dig out of the ground sodium metal because it's already reacted with water and oxygen in the environment to form sodium hydroxide, which is a base, hence the term alkaline. Same thing with potassium, same thing with calcium. All right, they're very reactive metals. Group 16 is known as the chalcogens, which means choking. Group 17 is known as the halogens, which is very reactive nonmetals. And group 18 is known as the noble gases, and they don't react. The key here is groups 1 through 17 kind of want to be like the noble gases if they can. If there is no set name, and every family, every group had a name at one point in time, but if there is no common name used anymore, we just call it the family of. So group 15, if you have a periodic table open and are looking, nitrogen's at the top, we call it the nitrogen family. Group 14, carbon's at top. All right, carbon family. Group 13, boron's on top, boron family, and so on. Okay, so molecules and molecular compounds. Things come together to combine to become more stable. All right, what is a chemical formula? Chemical formula is comprised of elemental symbols and numerical subscripts to show essentially how many of each atom is bonding in said formula. There's something called empirical formula, We'll talk about that in chapter 3. That's a lowest ratio possible. We're going to look at a molecular formula. So chemical formula is a general term. We're going to be looking at the molecular formulas of things, which actually show the exact number of atoms of each element in a compound. Structural formulas we will get into either at the end of Chem 1 or the beginning of Chem 2, most likely the beginning of Chem 2. And that actually shows the actual bonding between said molecules or atoms in a molecule. Okay. So what we're going to talk about is the formation of something called an ionic bond. And in order to do that, we need to talk about ions. Okay. An ion, and we kind of talked about it in a last presentation, but an ion is something that loses or gains electrons, thus gaining, let's not use gain again, let's use obtain. How about that? 50-cent word right there. Thus obtaining attaining a charge. There's two types of ions. A positive ion is known as a cation. Negative is known as an anion. Where I am on the periodic table will determine whether I'm a cation or an anion. My cations are usually my metals, and my anions are usually my nonmetals and metalloids. Okay. And it's all determined by how many electrons I'm going to lose and how many electrons I'm going to gain. So, let me pull up a periodic table again. All right. So if I look at my periodic table again, and I really suggest you have a periodic table out while we're talking about this, where I'm located on the periodic table is going to determine if I lose or gain electrons, how many I lose or gain, okay, and thus what charge I am. Now my goal is to be a noble gas. I want to be a group 18, or look like a group 18, I should say, electronically, with the number of electrons. So here's what we have to understand. Through all the experiments that I said, if you guys wanted to read about them and everything, here's what they found out. They found out again that the nucleus has the protons and the neutrons. And then outside are the electrons. Okay? Now, the electrons keep adding, okay, layer by layer by layer by layer by layer by layer. When one layer has the total amount of electrons, and you don't have to worry about that right now, but when one layer has the total amount of electrons needed, the next layer starts. The outermost layer is known as the valence shell. Therefore, this would be my valence electron. Okay. This is the electron that or the shell or area that I'm going to use to form bonds. These are the electrons I'm going to give up, or this is the area where I'm going to gain electrons, all right, in order to look like a noble gas. Now, as I get bigger and bigger and bigger and bigger and bigger, the layers get more and more and more protons go in, more neutrons. So drawing it out this way gets a little tedious to figure out how many valence electrons I have. Well, here's the fun part. Number one, how the heck am I supposed to know how many valence electrons I have? Well, for my main group elements, 1, 2, 13 through 18, the number in the ones position tells me how many valence electrons I have. So group 1 has 1 valence electron, group 2 has 2 valence electrons, group 13 has 3, and this is why I like the old numbering. And this is why I like this book. 1A, 2A, then it would jump to 3A. Group 13 has 3, group 14 has 4, group 15 has 5, 6, 7, and 8, all the way up to group 18. And the way we represent that is, okay, so we're going to have group 1. All right. We'll have 2. We'll have 13, 14, 15, 16, 17, 18. Okay. We represent it by something called a Lewis structure or a Lewis element. All right. What you do with the Lewis element to show the Lewis dot, all right, of the element, draw the element symbol out and imagine a box around it. Each side of the box can hold 2 electrons for a total of 8. You can't pair them up until they absolutely have to, so each side of the box has to have 1 electron. Well, let's start with, essentially, if we're looking at the periodic table, let's start with period 2 and look at lithium. Okay, lithium is a group 1. It has 1 electron. And I don't care where you start when you draw out your electrons. I really don't. Some people say start here and go clockwise. I don't care. Beryllium is next. It has 2. Boron, since it's in group 13, has 3. Okay. Group 14 is carbon. It'll have 4. Group 15 is nitrogen. Now realize what I did with carbon. 1 on each side. Group 15 has 5. Group 16 has 6. Group 17, which is fluorine, has 7. And group 18, which would be neon, has 8. Okay. Now, let's go right below it. And this is why they're families, and this is why they act similar. Sodium is going to have 1. Underneath beryllium is your magnesium. Going to have 2 because it's in group 2. Boron, underneath it is aluminum. Go from a non-metal to a metal, or a metalloid to a metal. Silicon, 4. Phosphorus, 5. Sulfur, 6. Chlorine, 7. And argon, 8. And we would continue on. Now, sodium's bigger than lithium, but the key is when we're looking at this, we just want to look at their valence electrons. Okay, so we look at the group number. Now, for my transitions, 3 through 12, don't worry about them. It all depends. It all depends on where we are, okay? So don't worry about my transition. This rule is for my main group elements. Now, our goal to become an ion is to look like a noble gas. I either want to look like the noble gas that's coming up or look like the noble gas that came before me. Now, we want to achieve the octet rule. We want to have 8 outer electrons. We want the happy magic 8. Okay, you'll see it as the happy 8, the magic 8, or the octet rule. What we have to realize is, and some of them only want 2 based on size, and we'll talk about that in the future at some point. But what we want to understand here is that I want to lose an electron, or do I want to gain 7? And that out underneath my valence shell is a stable, happy shell. So I'm lithium, I'm sodium. I have a choice to get that happy magic 8. If I lose one, my shell underneath is happy. Or I can gain 7. Well, the elements want to do the shortest path. So lose 1 or gain 7. Lithium and sodium rather give up an electron, and by doing so, they'll become a +1 charge, which means anything in group 1 will have a +1. Group 2, 2 valence electrons, lose 2 or gain 6. It's a lot easier to lose 2. And a lot of places, instead of writing +1, so I'll just say, I think this book does it this way, so I'll be consistent. They write it like this, a 2+ charge. Boron and aluminum. Lose 3, gain 5. I rather lose 3. So everything in group 13, for the most part, will be 3+. Let's skip 14 for right now. And now we get, 14 is our border. We go to 15. Lose 5 or gain 3. Now it becomes easier to gain. Gain 3, gain 2, gain 1. And since we're talking about electrons, that's why gaining, so these gain, these lose. That's why we become positive when losing and negative when gaining. And these guys are neutrals, so they don't do anything. No reaction. Okay, because they already have the happy magic 8. Then we get to group 14. It all depends on what element you're talking about. It could be a +4, it could be a -4. They could do both since they're halfway in between. Okay. So my tendency to lose and gain depends if I'm an... So really my metals want to lose and become positively charged, while my non-metals want to gain and become negatively charged. My metals lose and become the noble gas electronically, based on electrons that come before it, and my non-metals become the noble gas that's coming up. All right, questions on this before I get into putting compounds together? Because this is the key to put compounds together ionically. Let me know before I move on. Okay. Then let's talk about putting them together. So, in order to form an ionic bond is a complete transfer of electrons from one thing to another. An ionic bond, 99% of the time, will be a metal with a nonmetal. It's not always the case. Sometimes there's exceptions, just like everything. Okay. So what happens is my metal wants to give up electrons. My nonmetal wants to gain, so they help each other out. Okay. So let's look at the simplest that everyone always starts with because we're used to table salt. Sodium has 1 valence electron. Chlorine has 7. It's in group 17. Sodium wants to give up 1. Chlorine wants to gain 1. It's a perfect marriage. Sodium gives up that one electron, no longer has possession of it. Chlorine says, I will take it on. And by doing so, chlorine picks up a negative charge because it picks up that extra thing, electron. Sodium, because I called it a thing, it's an electron. Sodium is positive, chlorine is negative, and it's that positive and negative that bring them together to form sodium chloride. Okay. Always draw your arrows from the electron that's being given up to the spot that it's going to. For those of you who have to take organic chemistry after you pass this, and then you pass Chem 2, and then see me for Orgo if you're that sadistic. All right. Then, okay, you always draw from the electrons to where they're going. How do I name it? Take the name of the metal, sodium. Take the root of the nonmetal, chlor, and then add IDE, sodium chloride. Okay. Now, if I'm going to give up electrons or gain electrons, it's an all or nothing proposition. Here's what I mean by that. I've got, let's say, magnesium this time. Magnesium's in group 2, therefore it has 2 valence electrons. And let's bond it with bromine, which is in group 17 also, which means it has 7 valence electrons. The number in the ones position tells you how many valence electrons for my main group. Well, magnesium says, hey, I'd like to give up 2 electrons. Bromine says, thank you, but I only want 1. Well, bromine's happy because bromine just picked up the 1 from magnesium. But magnesium is ticked off because magnesium either wants to be as it is on the periodic table with 2, or it wants to give them all up and be the happy magic 8 like a noble gas. So in order to do that, I need to introduce another bromium. Or bromine, I should say. All right. All right. Now, both bromines are happy, magnesium's happy, and we write our chemical formula like the following. MgBr2. And this would be magnesium bromide. Magnesium bromide. Now, doing it this way is perfectly fine, but it can get a little complicated. So let's look at another example. Here's aluminum, group 13. Here's oxygen, group 6. Okay? Oxygen has 6 valence electrons. Sorry, group 16. See, I'm going old school. My brain still works a little bit that way. Aluminum wants to give up 3. Oxygen wants to gain 2. So aluminum says, here you go. Take. Oxygen is happy. Aluminum still has 1, isn't happy. So what do? We bring in a new oxygen. Yay. Okay, aluminum says, yes, I get to get rid of this one. Oxygen says, I'll take it. But oxygen says, hold on. I'm short. I need another one. I'm not happy. So we introduce another aluminum. And aluminum says, well, here you go. And oxygen says, great, I'm happy. But this aluminum says, this sucks. I gave up 1 and I want to give up 2 more. So what do? We got to draw another oxygen in. Okay, we draw another oxygen in. And doop, like so. And we're left with Al2O3, which is known as aluminum oxide. That's one of the worst M's I ever drew at the end of aluminum there. We'll do it a little bit better. If you're British, you call it aluminium. I've heard it called that before. Okay. But that gets a little tedious. Can I make it easier? Sure. We can make it easier as long as you know what your charges are. Okay, and that's why I went over that. Aluminum's in group 13. It has 3 valence electrons. Therefore, anything in group 13 is a 3+ charge. Oxygen is in group 16. Go back to what we just talked about. If you have to rewind, go ahead. Oxygen is a 2-, another beauty of using YouTube as opposed to Zoom and all that fun stuff. Bring your charges down and make them the subscripts of your other ion. Al2O3, Al2O3. Magnesium is in group 2 plus, is a 2+ in group 2. Bromine is a -1. Crisscross, it's called the crisscross method. MgBr2. I didn't use the colors there, but just to stay consistent here. Very patriotic on our board today. There we go. MgPr2, Br2. All right. So you can do the crisscross method. If they end up being the same, then you have to reduce them. For instance, magnesium bonding with oxygen goes a 1-to-1 ratio. So it's MgO. If I do the crisscross method, Mg2 plus O2 and I go to crisscross, I would end up with Mg2O2. That's not right. It's MgO. You have to reduce it. Okay? Questions on this? Questions on how I can get them to bond with one another? The key is you're looking for something to accept all the electrons and something to be able to donate all the electrons, to make each side happy. So what about my transition elements? What about iron? What about lead? What about those? How do I figure out? Well, there's 2 ways. One, the group number will tell you. However, some of them have multiple. And what I mean by that is this. Okay, if I were to name these, I take the name of the metal and then oxide. So this would be iron oxide. This is also iron oxide. The thing is, they're both 2 different compounds. Okay. This is FeO and this is Fe2O3. In order to distinguish between them, we use the charge of the iron to distinguish between it. So, oxygen's a 2-. Now, here's how you figure out the charge. Listen to me, okay? Listen really good here. Here's how you figure out the charge on your transition element. You know the charge on oxygen is 2 minus. Take this, all right, and multiply it by the subscript, and then divide by this subscript, and make it a positive whatever. And what I mean by that is this. 2 minus times 1, divide it by 1, and make it a positive, so that's a plus 2. This is iron. Now you have to use Roman numerals. Okay? And if you don't know your Roman numerals, here we go. 1 is I. 2 is II. 3 is III. 4 is IV. Okay? 5 is V. 6 is VI. 7 VII. 8 VIII. 9 IX. 10 X. We'll never have to probably go up to 10 or 9, but just for completeness, 1 through 10, use the Roman numeral. So let's try that over here. Oxygen is a minus 2. A minus 2 times 3 is a minus 6. Divide it by 2 is a minus 3. Then turn it into a positive. Okay. Plus 3. Now, you might have learned in school at one point, you could come back in like grade school, in high school, or if you're retaking this, you can go this way and do the reverse of the crisscross. It'll work as long as there's subscripts. Because if there is no subscripts, you'd say this is iron 1, and it's wrong. So this is iron 3 oxide, iron 2 oxide. The Roman numeral tells you the charge. So your group number will tell you your charge. If there's a Roman numeral, that tells you the charge. But what if I'm a transition element and I don't have a Roman numeral? If I'm a transition element and I don't have, so I'm in group 3 through 12 and I don't have a Roman numeral, my group number tells me my charge. So, for instance, group 3, scanadium and yttrium, they don't have a Roman numeral when they're written. They are a plus 3 because they're in group 3. Silver doesn't usually have a Roman numeral. If it doesn't, plus 1. If you're naming a compound, okay, and you're not sure if it's a transition element and you're not sure if it should or shouldn't have a Roman numeral, I'm not going to make you memorize which ones have Roman numerals and which ones don't. When in doubt with a transition, put a Roman numeral. Do not put a Roman numeral for main group elements. Okay? So, let's try another one. Let's do this. Copper 1 bromide and copper 2 bromide. So, bromine is a minus 1. Copper 1, Cu, and since it's copper 1, plus 1. Bromine's a minus 1. It's in group 17. Copper 2 is a plus 2. Now do your crisscross. Oops, lost my top. Do your crisscross. Down, down. CuBr. CuBr2. Are we okay? So transition elements need Roman numerals. Now with iron and copper, okay, I want to point out something that's a little archaic, but it's still used today for iron and copper for whatever reason. Iron 2 is known as ferrous, so you may see iron 2 written as ferrous oxide. Iron 3 is known as ferric. The higher gets the IC, the lower gets the OUS. So this could be also known as ferric oxide. Down here, this would be known as cuprous, copper 1. Okay, cuprous. And this would be known as cupric. Higher I, low O. Okay. Now, that's the start to naming ionic compounds. I'm going to finish this up on Monday and then start chapter 3. On Monday, okay, there's a table, it's in there, of polyatomic ions, it's called. It's in the slides, and it's also on page 72. It's table 2.5. You should familiarize yourself with said table. Okay. Now, homework that deals with these ions and things like that. Okay. What was the last homework problem I gave you guys? Because I don't want to repeat. Can someone tell me what was the last one I gave you on Monday? $2.46, thanks. Okay, so we are going to go to page 89. $2.51 to $2.59. $2.70 to $2.73. And then page 90, 2.84 to 2.89. Okay. I'm going to say our exam's going to be Thursday. That's going to be my guess. Our exam's going to be Thursday, but we're going to have new lectures on Chapter 3 on Monday and Wednesday. Now, come Monday, if you say, no, we want to take the exam on Tuesday, I'm fine with that, but I'm going to have a feeling you're going to want to push it to Thursday.